Hello and welcome to the independence of the complement theorem. It is a quaint little theorem which says essentially that given some two independent events, given some two independent events, one is not only independent of the other, but it is also independent of the other's complement. In other words, if an event is independent of another event happening, it is also independent of it not happening, which I would say coincides with our intuition. That is what we would intuit. And let's give it some mathematical foundation. Well, given some independent random events, AB, then 1, A, B complement are also independent. Moreover, if the probability of B is positive, then the probability conditioned, this is number 2, then the conditioned probability of A happening after B or under B is just the probability of A, which again is precisely what we would intuit. If B is independent of A, then pardon me. Pardon me. What I meant to say is that it really is what we would intuit, because B is independent of A, and this expression basically tells us if B happened, what is the chance of A happening? Well, if they are independent, then that B happened has no bearing on whether A will happen too. So it is precisely what you would expect. And now on to the proof. It is very simple. So, regarding the second point, it's easier to prove. So, number 2. Well, this one is trivial. So, we simply use the definition of a conditioned probability. So, we have A under the condition of B is equal to, by definition, P of A intersected with B divided by PB. But since the events are independent, we know that this is equal to the product PA times PB with the same denominator. And the reason for it, again, is quite intuitive. What is the chance that both the independent event of A happens and the independent event B happens? Well, that's simply this. That's secondary school stuff. And here we'll cancel out the probability of B and we simply obtain the probability of A, which is what we wanted. Now, regarding the first point, this one will take a little bit more time. It will take us a little bit more time to prove, but it is still quite manageable. So, what shall we do? Well, we want to show that A and B complement and the complement of B are independent. Well, okay. Well, and that's actually what we even used up here. That is the definition of two independent events. We will use, by definition, we want to show that the probability of A intersected with the complement of B is equal to the product of the probability of A and the probability of the complement of B. How do we get to this? Well, again, we use the definition. So this is all more or less, it's an exercise more than anything. So the probability of A intersected with the complement of B is equal to the probability of A without A intersected with B. This one is interesting, but one needn't do more than simply draw two very simple Venn diagrams to verify this. So we can do this briefly. Well, the first one, the left-hand side, well, given some sets A and B, the intersection of A, which is here, and the complement of B, which is all this, we find that the intersection is precisely this. And if we draw the second situation, we will have that A without A intersected with B, which is this middle bit, again yields this chunk with the right hand side bit cut out. So by a proof by picture, we get this equality, and using the using the sigma or finite additivity of probability, we get that this is equal to P of A minus P of A intersected with B, and this using the definition of two independent events, we arrive that this is PA minus PA times PB, and this is nothing more than PA times 1 minus PB, which is by definition PA times P of the complement of B, which concludes the proof.